Welcome, ladies and gentlemen. May I have your attention, please? Thank you. So we need to be able to calculate the probability that two events occur, right? Whether they're mutually exclusive or not mutually exclusive. And we saw the addition rule was our tool to do just that. And so if two events are mutually exclusive, think about what that means. Right? If they're mutually exclusive, with our Venn diagram picture, it means that they cannot occur at the same time. They're not overlapping. And so to find the probability that one or the other occurs, that is the probability that A or B occurs, is easy. We'll simply sum together their individual probabilities. That is the probability that event A occurs plus the probability that event B occurs. The addition rule holds true for overlapping events as well. It's just that if they're overlapping, right, then that overlap gets counted once in your original probability that the first event occurs. It gets counted again in the probability that the second event occurs. And so what do we need to do? We need to subtract off that overlap because it's been double counted. It got counted once in the first set, once in the second set. So we need to subtract over that overlap one time. And that is the probability that A and B occur simultaneously. And that's still the addition rule. It just now takes into account that those events were not mutually exclusive. The multiplication rule is different entirely. The multiplication rule talks about for independent events. That is, if the likelihood of one event does not influence the likelihood of the other event, then those events are said to be independent. So think about our example in last activity when you were rolling dice. If you were rolling dice twice, does the result on your first roll influence the outcome of the result on the second roll? No, those events are not connected, right? Your outcome on the first roll in no way influences the outcome on the second roll, and so those events are independent. If they are independent, then we can calculate the probability that A and B occur simply by multiplying their individual probabilities together. And that's exactly what you earned on your activity 2, those last two stamps, right? The multiplication rule holds true for independent events. We can calculate the probability that A and B occur simply by multiplying their individual probabilities together. So that would be a probability of A times the probability of B. Today we're going to go ahead and see how we can use these to calculate some probabilities in some real world situations. We're going to deal with households in Wanakee who own cats or dogs. Okay, so let's go ahead and take a look at our final exam information one more time. You know, tonight, Wednesday the 25th from 3:45 to 5 o'clock p.m. we've got our final exam study night. So you can bring your review packet, you can come, you can ask questions, you can work with each other, you can ask questions, and make sure that you're good to go for the final exam. Part 1 then is next class. You'll be taking the non-calculator portion of your final exam, the last regular day of class. For us, that's the 27th A day. B day students are taking that on the day after Memorial Day. That's Tuesday the 31st. Part 2, calculator allowed. That's the first day of exam, second time slot. Everybody, let's make sure we fill in our room number. For us, 2A, we're in room 1518. So 1518 with Mr. Butters is ours, and we had this last time, and so you don't have it again. But for us, we're in room 1518. Everybody good? Make sure you bring your completed review packets. That'll be your ticket to take the exam on that Wednesday, June 1st, as well as pencils and calculators so you're ready to go. Questions about the exam logistics? Okay, I uploaded answer keys then for the review packet with updated parabola graphs from page 2. And so please make sure you check out the answer keys, which are posted on our Moodle course website. You can click on the hyperlink there, and it shows the worked out solutions for each of those problems on your review packet, and that can help you as you check your work as you prepare for the final exam. Let's go ahead and pause the recording now, though, and get yourself credit for your worksheet number 2. So our addition rule, that is the probability that event A or event B occurs, right? When two events are mutually exclusive, it's easy to calculate the probability that event A or event B occurs. We'll simply sum together the individual probabilities, and that's why it's called the addition rule. If they're not mutually exclusive, right, we still use the addition rule. It's just that if they're not mutually exclusive, it means they could occur at the same time. And so the first event, right, is going to count that overlap once in the probability that A occurs then the probability the second event occurs is going to count that overlap again. We've counted that overlap twice, therefore we need to subtract it off once to make sure that we get the accurate probability that event A or B occurs. So that's exactly what we did in our activity 1, the addition rule. What about the multiplication rule? Well, the multiplication rule holds true only if two events are independent. If two events are independent, that is, the result of one event does not influence the likelihood of the second event occurring, then we can simply multiply their individual probabilities together to get the probability that A and B occur. So this is the multiplication rule. This is the addition rule. Let's go ahead and see if we can't use those in context. Events A and B are independent if the probability of A does not affect the probability of B. We've seen how the two consecutive rolls of dice, right, are independent events. The result of the first roll does not influence the result of the second roll. If two events are independent, then the probability that A and B occur is simply the product of their individual probabilities, and those were two stamped eligible items last class. One way to verify that two events are independent is to find the probability of A and find the probability of B, and then find the probability of A and B. If they're independent, then the multiplication rule has to hold true. That is, the probability of A and B occurring has to be given by the product of their individual probabilities. Let's see what that looks like. We can almost see what that looks like. First, it makes sense then that dependent events, right, are events where the outcome of one does influence the likelihood of the other event occurring. So events A and B are dependent if the probability of A does affect the probability of B. When two events are dependent, then the probability of A and B doesn't equal the product of their individual probabilities. You could think about two events, right? Going to a barbecue, having a hot dog and having ketchup as two separate events. I would posit that the outcome of one event is going to influence the likelihood of the other event. For example, if you have a hot dog, that might influence your decision whether or not to have ketchup as well, right? As opposed to you having the pulled pork barbecue. You know what I'm saying? Then maybe you won't have ketchup. So those would be dependent events. All right, let's suppose that 50% of households in Wanakee own a dog or a cat. Okay, so 50% of the households in Wanakee own a dog or a cat. If the probability of owning a dog in Wanakee is 45%, and the probability of owning a cat is 20%, are these two events mutually exclusive? Mutually exclusive, recall, refers to those events occurring at the same time or not. So if they're mutually exclusive, it means the two events do not occur at the same time. Think about the probability of owning a dog. Right? So the probability of owning a dog in Wanakee, let's suppose that's 45%. And we'll think about the probability of owning a cat, and that was 20%. And yet, the probability of owning a dog or a cat is 50%. Can these two events be mutually exclusive? Go ahead and decide with your partner. Go ahead and decide if these events are mutually exclusive. All right, what do you guys think? Jacques and Megan.
They're not mutually exclusive.
Stop right there. Raise your hand if you agree that they're not mutually exclusive. Not mutually exclusive. Excellent. And why did you guys decide that they're not mutually exclusive?
Because you could have a dog and a cat.
They could occur simultaneously. You could have a dog and a cat at the same time. What about with the numbers? What about with the numbers? Andrew?
They don't add up to 50, they're more than 50.
Absolutely. If they were mutually exclusive, the probability of A or B occurring, right, 50%, would equal the sum of their individuals. Does 0.45 plus 0.20 equal question mark 0.5? No way, Jose. And so we've seen that they are not mutually exclusive. Otherwise, the probability of A or B occurring would have to be the sum of the individuals, and it's not, clearly. Good. So what's the probability that the household has both a dog and a cat? Well, in order for that to work out, we have to subtract off the overlap. How much overlap must there be? That is A and B occurring at the same time? We'll check it out. we've got to get from 0.45 plus 0.20, which is 0.65 or 65%. We need to get to 50%. So what would we have to do? Well, what percent of households then must own both a dog and a cat, right? What's that going to have to be? Like,
15%.
absolutely. So the intersection of events A and B, that is owning a dog and a cat simultaneously, must be 15%. Nice job. Are these two events independent or dependent? So independent or dependent? Well, we can get that by considering the product of their individual probabilities. We know that two events are independent if the product of their individual probabilities is equal to the probability that A and B occur simultaneously. We just saw, right, that the probability of A and B occurring simultaneously is equal to 15%. We want to see if that equal question marks the probability of event A times the probability of event B. Well, what's the probability of event A owning a dog? Right? What was the probability of event A owning a dog? Hans? Good. So that would be 0.45 as a decimal. What was the probability that a household owns a cat in Wanakee? Maya?
0.20.
Good. 0.20. Let's go ahead and see if the probability of owning a dog and a cat, that's 0.15 or 15%, is equal to the product of the individual probabilities. So we'll simply go to our calculator and we'll do a quick check. 0.45 times 0.20, enter. Does that equal question mark 15%? No, it equals 9%. So we verified mathematically that these events are not independent. Well, contextually, that makes sense, right? Do you think that owning a cat and owning a dog would be independent events? That is, the likelihood of one, right, does not influence the likelihood of the other? Go ahead and talk with your partner. Do you think those two events, regardless of numbers, would be independent or dependent? Okay, so what did you guys think about owning a dog versus owning a cat? Do those events seem to be independent or dependent in context, regardless of the numbers? Right, what did you guys think? Nathan and Casey?
Dependent.
Dependent, why did you think that?
Because if you have a dog, then you probably like animals and may as well get a cat.
Absolutely, right? If you own one kind of pet, I would guess that it might be more likely you own another kind of pet as well, versus those households that don't have any pets, any animals. Maybe someone's allergic to pets or to the dander or something like that, and then you're not going to get any pets. But once you have one, the likelihood that you have others would likely be influenced and would likely increase, would be my guess. Awesome, thank you guys. All right, let's take a look at the Venn diagram then to illustrate this. So the probability of owning a dog, right, in Wanakee was 0.45%, so we can go ahead and make that the green circle here. And then the probability of owning a cat in Wanakee, we can make that the blue circle here, and that was 20%. The probability of owning a dog or a cat was 50%, and so this overlap portion right here, the probability of owning a dog and a cat must be our 15%. Then 0.45 plus 0.2 minus 0.15 equals our desired 50%. That is to say, our addition rule holds true. 0.45 plus 0.20 minus our 0.15 equals the probability that there's a dog or a cat in the house. Nice job. Questions about our Venn diagram visual representation of the scenario? That's pretty sweet. Okay, we're going to close it out today with the counting principle, which involves multiplication, to set up with some independent event probability calculations versus dependent event calculation. First, let's suppose that our one breakfast menu includes a choice of meat. We've got bacon or sausage. Choice of eggs, we could have scrambled, sunny side up, or over easy. Choice of side, pancakes or hash browns, and then choice of beverage, milk, juice, or coffee. What's the total number of breakfast combinations? The counting principle is very powerful. It's a way where we can systematically determine the number of possibilities for a given situation simply by considering, right, tree diagrams, but simplified through multiplication. In other words, if I've got 2 choices for my meat, I've got 3 different choices for my kind of egg, 2 choices for a side, and then 3 choices for beverage. It would take a long time to list all the possible, right, orders. However, if I simply take the number of meat choices, 2, times the number of egg choices, 3, times the number of side choices, 2, times the number of beverage choices, 3, I can get the total number of possible orders simply by multiplying them together. So it's that easy. Our counting principle says take the number of choices and multiply them together. So 2 meat times 3 eggs times 2 sides times 3. Looks to me like we've got a whopping 36 different orders are possible. Is that right? So we've got 36 different possibilities here if you're just sticking with this menu. So the number of ways, one element from A and one element from B, we can utilize this counting principle now in the context of outcomes. So let's flip a coin 2 times. What then is the probability of getting heads first, followed by tails on the second flip? Well, are these events independent or dependent? That is, does the result of my first flip influence the outcome of my second flip? Are these events independent or dependent? Kendall?
Dependent?
The outcome of the first flip influences the outcome of the second flip?
Oh, no.
No, right? They're independent events because the outcome of the first does not influence the outcome of the second, right? They're an independent event. Each time I flip it, we've got the same probability that heads will come up versus tails come up. What is that? Well, it's 1/2. So I can do 1/2. On the first flip, there's a 1 in 2 chance that I get a heads. And on the second flip, well, there's also a 1/2 chance that I flip tails on the second flip, which means the probability of flipping heads followed by flipping tails is 1 in 4, 0.25 or 25%. What about rolling a die 2 times? Are these events independent or dependent? Does the result of the first roll influence the outcome of the second roll? Well, they are independent, so we can multiply their individual probabilities together. The probability that I get a 3 on the first roll of a fair 6-sided die is 1 in 6 chance, followed by the probability that I roll a 4 on the second roll. Uh-oh. We don't want that. Pesky little bugger. We want this. The probability that I roll a 4 on my second roll is also 1 in 6. So to roll a 3 followed by a 4 in that order looks like a 1 in 36 chance. We can extend this now for longer chains of events. If the probability is the same each time, you can take the probability of that event occurring and raise it to the number of events as your exponent. In other words, this would be 1/2 times 1/2 times 1/2. So this would be 1/2 to the 3rd power. And that'll show up on your probability review worksheet too. You could expand that as 1/2 times 1/2 times 1/2. You could do a parentheses all to the third. In any case, we can see that would be a 1 in 8 chance. 12.5%. Awesome. All right, so now we do a big chain. Let's let H be the event heads shows after flipping a fair coin. Let T be the event tails shows after flipping a fair coin. With replacement, that's synonymous with independent. The first flip has no effect on the likelihood of the second flip's outcome, or the third flip's result, or the fourth flip's. And so I can take the individual probability, 1/2, and raise it to the how many events? 3, 4, 5, 6, 7 to the 7th. Oh my God. If only I knew what 1/2 to the 7th was. About 128. Probability of rolling a die 4 times and getting a 5 each time. You guessed it. The probability of rolling a 5 on a single roll, 1 in 6 chance. How many 5s in a row? 4. So 1/6 to the 4th. Don't know what that is. We have a 6 to the 4th on there. 216 followed by 1296. Thank you. And yes, back to our classic standard deck of playing cards shuffled, and we're going to go ahead and reach in and draw a king, right? Then we're going to put it back, shuffle, and then draw a king again. So this is with replacement. All the probability that I draw a king on the first draw, there's how many kings? 4 kings out of 52 cards. Put it back, shuffle, close my eyes, draw a second card. There's still 4 kings. There's still 52 cards. I can multiply those two together and get the result. All right? It's all right? Math bracket?
Yes.
Awesome. Thanks, Rachel. Okay. Cool. What's different? What if we don't replace that card? What? What if we don't replace the first king? So we reach in to our randomly shuffled deck. The probability we draw a king on that first draw is still 4 out of 52. However, the likelihood of the second draw has now been influenced by the outcome of that first draw. How many kings remain in the deck if I do not replace the first? Well, for that second draw now, how many kings are there? There's only 3 out of how many cards remain? 51. And so we can multiply, right, our probabilities together. However, the second event's likelihood is influenced as a result of the first event occurring. Awesome. I'm going to math frac this time. By golly. One over 221. Goodness. And lastly, probability 2 black cards in a row. So let's think about how many black cards there are. Well, gosh, for the first draw, half of the deck, right, are black cards. So 1 in 2 chance, or 26 out of 52. However, given that I've drawn a black card and I did not replace it, now how many black cards remain? Well, now only 25 black cards remain for that second draw out of 51 cards. This is definitely a job for Math Frac. $25 out of 102. questions you have about our multiplication principle with replacement versus without replacement. Rachel?
I thought it was the probability of them multiplied, but then also the probability of events added together to the square.
Okay, so A, B, and C are not number of events occurring. They're descriptions of events, right? So if you're going to calculate the probability that A occurs, we're not taking A divided by A plus B plus C. We'll simply write P of A, the notation for the probability that event A occurs, particularly when we're not given numbers or sets for the Bellwork. So probability of A multiplied by the probability of B, right, is going to be the probability that A and B occur if the events are independent. If they're not independent, those events do not hold true. Okay? Let's go ahead and take a look at our final assignment. So we've got our final exam review that we've been working on intermittently. We've got our probability review worksheet due next class. Non-calculated final exam portion is our last day of regular scheduled class next time. But first, right, we need a stamp check. And so we're going to do our final stamp check of the year, Unit 9, our mini unit. I'm going to go ahead and stop the recording now so that we can take care of our stamp check, and then you're going to have some work time on the semester review.